Hey everyone, and welcome. If you've ever sat through a physics class, you've probably had one particular equation drilled in your head. But what we learn in school, that's often the super clean, perfect world version of the universe. Today, we're going to pull back the curtain and see how physics really works when things start to get a little messy. So let's dive into what makes real-world physics so fascinating.
And here it is, the big one. Force equals mass times acceleration. This right here is the absolute bedrock of classical mechanics, Newton's second law. It's elegant, it's powerful, and it perfectly describes how a soccer ball flies or how a car speeds up. But, and this is a big but, there's a catch. This version of the equation, it only works in a perfect world, one with zero friction and where an object's mass is always the same.
So, what does happen when we step out of that pristine textbook world and into our own? What about the air that's constantly pushing back on us? Or what about an object that's actually losing or gaining weight as it moves? Well, that is where the real fun in physics actually begins. And this contrast is everything. In one corner, you have ideal physics, things moving in a perfect vacuum, objects with a mass that never, ever changes. And in the other corner, you have the real world, where the air literally pushes back on you. And yeah, mass can totally change. So let's tackle these complications one by one.
Okay, first up, air resistance. This is a force we all feel every single day, right? Whether you're riding your bike into the wind or just walking on a blustery day. In physics, this has a name. It's called a resistive force, and it completely changes the game for how things fall.
A resistive force, or as it's often called viscous drag, does exactly what it sounds like. It resists motion. But here's the crucial part. It isn't some constant steady force. Nope. The faster you move through the air, the harder the air pushes back. And this creates this incredible tug of war with the force of gravity.
So, how does this play out? Just imagine something starting to fall. At first, gravity is the undisputed champ. It's pulling way harder than the air is pushing back. So the object accelerates. But as it picks up speed, that upward push from the air gets stronger and stronger and stronger, until finally that upward push from the air perfectly balances the downward pull of gravity. At that exact moment, the net force becomes zero. Acceleration stops cold, and the object just keeps falling at a steady, constant, maximum speed. We call that terminal velocity.
This balance is absolutely key. When those two forces cancel each other out, velocity just flatlines. It's the whole reason raindrops don't smash into us like tiny little bullets, and it's exactly how parachutes work. It's like our atmosphere has its own built-in speed limit.
So, how fast is this speed limit? Well, for a paratrooper with their chute wide open, terminal velocity is a nice, gentle 24 kilometers per hour. That's about 15 miles per hour. Totally slow enough for a safe landing. And get this is the part that's pretty wild. It only takes about 3.3 seconds after opening the parachute for that paratrooper to slow down to that safe landing speed. That balance between gravity and air resistance happens incredibly fast.
Okay, so we've upgraded our thinking to include air resistance. Awesome. But what about that other little ideal world assumption we made? What happens when the m for mass in our favorite equation isn't a constant at all?
This question, right here, just blows the doors open to a whole new world of physics problems. We tend to think of objects as having one fixed mass, but in so many real-world systems, that's just not true. So, how does physics even begin to deal with an object that's constantly changing how heavy it is?
Just think about it for a second. A raindrop falling through a cloud is actually getting heavier as it collects more water. A hot air balloon can climb higher by dropping sandbags, making itself lighter. And then there's the most dramatic example of them all, a rocket, which is literally shedding tons of mass every single second as it burns fuel.
To wrap our heads around this, we have to go back to the truer, more fundamental form of Newton's second law. See, force isn't just mass times acceleration. It's actually the rate of change of momentum, and momentum is just mass times velocity, or mv. Now, when the mass is constant, this whole thing simplifies down to our old friend F equals ma. But when mass isn't constant, we have to account for the change in both mass and velocity.
And that brings us to the ultimate physics challenge, a system that has it all: enormous forces, insane changes in velocity, and a rapidly changing mass. I'm talking, of course, about a rocket launching into space.
This is such a classic brain teaser, right? We're so used to pushing against something to move. We push against the ground to walk, a boat pushes against the water. So how on earth does a rocket accelerate in the complete emptiness of space? Well, the answer is all about something called the conservation of momentum. It is just genius when you think about it.
A rocket works because it brings its own stuff to throw. It literally throws its own mass, its fuel, out the back at unbelievable speeds. The laws of physics say that the total momentum of the whole system, the rocket plus its fuel, has to stay the same. So, as a massive amount of momentum gets blasted backward as exhaust, an equal and opposite amount of momentum has to push the rocket forward. It's basically pushing against its own fuel.
And this is the legendary Tsiolkovsky rocket equation. You do not need to be a math whiz to appreciate how cool this is. This single equation just beautifully captures that whole exchange of momentum. It tells us exactly how a rocket's acceleration is tied to how fast it shoots out its fuel and how quickly its own mass is dropping. This is the math that took us to the moon.
So what's the big takeaway here? It's not that F equals ma is wrong, not at all. It's just one tool, a really, really important one, in a much bigger toolbox. Real physics is about knowing which tool to pull out to describe the world as it actually is, messiness and all.
Today, we added 2 huge new tools to our kit. To handle the air pushing back, we use the idea of terminal velocity, and that explains how a paratrooper can land safely. And to deal with the changing mass, we use the conservation of momentum, which is the secret to how a rocket can even get off the ground.
You see, these fundamental laws, when you apply them to the complicated, messy, real world, they give us this incredibly powerful lens to understand everything, from a single falling raindrop all the way to humanity's journey to the stars. The only question left is, what are they going to help us discover next?